Hurricane Katrina, 2005. 1,800 people dead. It lasted 6 days, then disappeared. Now look at this. Jupiter's Great Red Spot. A storm so large it could swallow 3 Earths. Winds over 400 kilometers per hour. And it's been raging for at least 190 years. Venus, where winds circle the planet in 4 days, but the planet itself takes 243 days to rotate. The atmosphere moves 60 times faster than the ground. Mars, a planet half the size of Earth with an atmosphere 100 times thinner. Yet dust storms cover the entire planet in darkness for months. This isn't weather. This is warfare. To understand why weather elsewhere is so extreme, we need to understand what normal looks like. Earth's atmosphere is 78% nitrogen, 21% oxygen, 1% everything else. About 100 kilometers thick from surface to space. But 75% of its mass is in the lowest 11 kilometers, the troposphere, where we live, where weather happens. Weather is driven by 3 things. 1. Differential heating. The equator receives more solar energy than the poles. Hot air rises at the equator, cold air sinks at the poles. This temperature difference drives circulation. 2. Rotation. Earth spins once every 24 hours. This rotation deflects moving air and creates the Coriolis effect, making storms spin. 3. Water. Liquid water evaporates, carries heat into the atmosphere, then releases that heat when it condenses. This phase change is the engine of Earth's most powerful storms. Simple, right? Not really. A hurricane forms over warm ocean water, at least 26.5 degrees Celsius, 80 degrees Fahrenheit. Warm, moist air rises. As it rises, water vapor condenses. Condensation releases latent heat. That heat makes the air rise faster. More air rushes in at the surface to replace it. Earth's rotation makes it spin. Feedback loop. Self-amplifying. Chaotic. Category 5 hurricanes have wind speeds exceeding 252 kilometers per hour, 157 miles per hour. The storm surge, water pushed ahead of the hurricane, can reach 6 meters, 20 feet above normal sea level. But hurricanes are fragile. Cut off the warm water supply by moving over land, and they die within days. Change the atmospheric wind shear, winds at different altitudes blowing in different directions, and they fall apart. Earth's most powerful storms last days, maybe 2 weeks maximum. They're temporary, localized, destructive but brief. Now scale that up. Remove the oceans, remove the land, remove everything solid. Make the entire planet a gas ball twice as massive as all other planets combined, and see what happens. Here's what we expected for gas giant weather. Bigger planet equals bigger storms. More energy, more convection, more chaos. No surface equals no friction. Nothing to slow storms down. They should last longer than Earth's. Fast rotation equals strong Coriolis. Jupiter rotates once every 10 hours. Saturn, 10.7 hours. This should create intense spin. For planets with atmospheres but no oceans, no water cycle equals weaker storms. Without water's phase changes to release energy, storms should be less intense. So explain these. A storm on Jupiter lasting 190 plus years, possibly longer. An atmosphere on Venus spinning 60 times faster than its surface. Global dust storms on Mars that engulf an entire planet. The solar system's weather doesn't follow Earth's rules. Let's find out what rules it does follow. Jupiter's Great Red Spot. An anticyclone, a high-pressure system rotating counterclockwise in Jupiter's southern hemisphere, currently about 16,000 kilometers wide, 1.3 times wider than Earth. But it's shrinking. In the late 1800s, it was 40,000 kilometers wide, 2.5 Earths side by side. Wind speeds at the edge, 432 kilometers per hour, 268 miles per hour. But recent measurements show gusts exceeding 640 kilometers per hour, 400 miles per hour, faster than any hurricane on Earth. First reliably observed in 1831. Continuous observations since 1879. That's at least 190 years. But here's the mystery. A 2024 study analyzed historical records and concluded that the permanent spot observed by Giovanni Cassini from 1665 to 1713 was probably not the same storm as today's Great Red Spot. That means the current storm is only 190 to 200 years old. But it might have predecessors. Jupiter might continuously generate massive storms in the same location. Between December 2023 and March 2024, NASA's Hubble Space Telescope watched the Great Red Spot continuously for 90 days and saw something unexpected. The storm isn't stable. It jiggles, like a bowl of gelatin. Over its 90-day cycle, the Great Red Spot oscillates, expanding and contracting, changing shape. Its longitudinal extent varies by about 1 to 2 degrees. That doesn't sound like much, but on Jupiter, 1 degree equals about 1,300 kilometers at the equator. The storm is breathing. Why? As the Great Red Spot accelerates and decelerates during its 90-day cycle, it pushes against the jet streams to its north and south. Those jet streams push back. The storm squeezes, expands, squeezes, expands. July 2024. Caleb Kevaney at Yale publishes research in Icarus explaining why the Great Red Spot is shrinking and why it has lasted so long. The Great Red Spot feeds on smaller storms. When smaller anticyclones merge with it, they add energy. The storm grows. But there are fewer small storms feeding it now than in the past century. Result? The Great Red Spot is shrinking. But slowly, very slowly. July 2022. The James Webb Space Telescope aimed its instruments at the Great Red Spot. Using the MIRI, Mid-Infrared Instrument, scientists mapped the storm's thermal structure. Discovery: the Great Red Spot is cold at its center. Center temperature: about 160 Kelvin, negative 113 degrees Celsius, negative 172 degrees Fahrenheit. That's cold enough for ammonia and water to condense out of Jupiter's atmosphere, forming thick clouds. JWST also detected phosphine gas, pH 3, inside the storm. Phosphine forms deep in Jupiter's atmosphere, where temperatures and pressures are extreme. Its presence in the storm suggests powerful upward convection, material from deep below being dredged up. And phosphine might explain the storm's red color. When exposed to sunlight, phosphine breaks down and could produce red-brown compounds. After 190 plus years, we're still learning what makes it red. Earth hurricanes die with cut off from warm water. Jupiter has no surface, no oceans, nothing to cut off. But Jupiter does have an internal heat source. It radiates 1.6 times more energy than it receives from the Sun. That excess heat comes from primordial warmth left over from formation, plus ongoing gravitational contraction. Jupiter is very slowly shrinking, converting gravitational potential energy into heat. That internal heat drives convection throughout Jupiter's atmosphere. Rising plumes of warm gas, sinking columns of cold gas. The Great Red Spot sits atop one of these convection cells. And unlike Earth hurricanes, which are powered by water condensation, the Great Red Spot is powered by internal heat from below, absorption of smaller storms, interaction with jet streams that compress and energize it. It doesn't need a specific fuel source that can run out. It just needs Jupiter's atmosphere to keep convecting, which it will, for billions of years. The Great Red Spot might shrink. It might eventually disappear. But Jupiter will likely spawn another, because the conditions that create it, internal heat, fast rotation, no surface friction, aren't going away. Venus rotates once every 243 Earth days. That's slow, incredibly slow. Slower than its orbit around the Sun, 225 days. Venus's day is longer than its year, but its atmosphere? The cloud tops circle the planet in just 4 Earth days. The atmosphere moves 60 times faster than the surface. Wind speeds at the cloud tops: 100 meters per second, 360 kilometers per hour, 224 miles per hour. Constant, unrelenting. Hurricane force winds wrapping around the entire planet. This phenomenon is called superrotation, and for decades no one understood how it worked. December 2015. Japan's Akatsuki spacecraft entered Venus orbit after a 5-year delay. Its mission? Map Venus's atmospheric dynamics. Between 2015 and 2020, Akatsuki tracked cloud movements in ultraviolet and thermal infrared. Scientists followed tens of thousands of cloud features, measuring their speed and direction. April 2020. Takeshi Horinuchi and his team published their findings in Science. They'd solved the mystery. Superrotation is driven by thermal tides. Here's how it works. Venus's thick atmosphere, 92 times Earth's surface pressure, absorbs enormous amounts of solar heat at the cloud tops, around 70 kilometers altitude. That heating isn't uniform. The day side gets heated, the night side doesn't. This creates a pressure difference. Air flows from high-pressure day side to low-pressure night side. But Venus rotates, slowly, beneath it. The Coriolis effect deflects the moving air, creating eastward winds. As these winds accelerate, they carry angular momentum from the slowly rotating surface upward into the atmosphere. Over millions of years, angular momentum accumulates in the cloud layer. Result? The atmosphere spins independently, decoupled from the surface, powered by the day-night heating cycle. But if thermal tides continuously accelerate the atmosphere, why doesn't it spin faster and faster forever? 2 forces counteract the thermal tides. 1. Planetary scale waves. These slow-moving atmospheric features occur on any rotating planet with an atmosphere, including Earth. They propagate westward, opposite the superrotation, and drain angular momentum from the fast-moving winds. 2. Atmospheric turbulence. Small-scale, chaotic motions at the cloud tops create friction, slowing the winds at Venus's equator. Thermal tides push. Waves and turbulence resist. The system reaches equilibrium around 100 meters per second. But equilibrium doesn't mean stability. Between 2006 and 2014, ESA's Venus Express spacecraft monitored Venus's cloud-top winds and detected something strange. The winds were accelerating. In 2006, average cloud-top wind speed was about 95 meters per second. By 2013, 105 meters per second. A 10% increase in just 7 years. 2024 observations from Akatsuki confirm the trend continues, with dramatic short-term variations. Sometimes clouds circle Venus in 3.9 days, other times 5.3 days. Why are the winds increasing? Why do they vary so dramatically on short timescales? February 2024. Research published in Geophysical Research Letters offers a clue. Mountain waves, atmospheric disturbances created when winds flow over Venus's highland regions, can propagate upward from the surface all the way to the thermosphere, 150+ kilometers altitude. These waves affect circulation patterns above the clouds. Venus's surface isn't smooth. Aphrodite Terra, Maxwell Montes, large highland regions. As super-rotating winds blow over these mountains, they generate gravity waves that ripple upward, potentially altering wind speeds above. Venus's atmosphere is more complex than we thought. The superrotation isn't just driven by thermal tides. It's modulated by the surface, by waves, by turbulence, all interacting in ways we're only beginning to understand. Mars's atmosphere is 100 times thinner than Earth's. Surface pressure, 600 pascals. About 0.6% of Earth's sea level pressure. That's barely there, a near vacuum. So you'd expect weak weather, right? Gentle breezes, maybe small dust devils. Wrong. June 2018. A regional dust storm on Mars escalated into a planet-encircling event. Within weeks, dust covered the entire planet. Sunlight reaching the surface dropped by 99%. NASA's Opportunity rover, powered by solar panels, went silent. Never woke up. How does a planet with almost no atmosphere create global dust storms? Mars has dust, lots of it. Fine particles of iron oxide, rust, cover much of the surface. Grain size? 1 to 10 micrometers. Small enough to stay suspended in even thin air. Mars has extreme seasonal temperature variations because its orbit is more eccentric than Earth's, and its axial tilt creates dramatic seasonal effects. During Martian summer in the southern hemisphere, the South Pole heats up rapidly. The North Pole remains cold. Temperature difference creates pressure difference. Air flows from high pressure to low pressure, from the warm pole toward the cold pole. Wind speeds? Up to 60 meters per second, 216 kilometers per hour, 134 miles per hour. That's strong enough to lift dust. Here's the key. Once dust gets into the atmosphere, it absorbs sunlight and heats the air. Warmer air creates stronger winds. Stronger winds lift more dust. More dust heats more air. Positive feedback loop. In 2018, a regional storm hit at the start of southern summer, the worst possible timing. The feedback loop kicked in. Within 3 weeks, the storm covered 25% of the planet. Within 2 months, it was global. Mars Reconnaissance Orbiter measured atmospheric opacity, how much sunlight gets through. At the height of the storm, opacity was over 10. Normal is 0.5 to 1.0. The sun was reduced to a dim glow. Surface temperature dropped, but atmospheric temperature increased. Global dust storms on Mars are rare. They occur roughly once every 3 to 4 Martian years, about 6 to 8 Earth years. Why not every year? Mars's elliptical orbit means southern summer coincides with perihelion, when Mars is closest to the Sun. Maximum solar heating plus southern summer plus dust availability equals perfect conditions. But even then, it doesn't always happen. 2024 research shows that global dust storms require strong temperature gradient, southern summer, pre-existing dust in the atmosphere from earlier storms, favorable wind patterns that connect different regions. All three must align. When the storm ends, and it always does eventually, dust takes months to settle out of the thin atmosphere. Slowly, gently, covering solar panels, burying rovers. Mars's atmosphere is thin, but it's enough. Enough to lift billions of tons of dust. Enough to engulf an entire planet in darkness. Enough to kill a rover. Titan, Saturn's largest moon. The only moon with a thick atmosphere, surface pressure 1.5 times Earth's at sea level. Composition: 95% nitrogen, 5% methane. No oxygen. Thicker than Earth's. Denser. Extending 600 kilometers above the surface. But colder. Surface temperature: minus 179 degrees Celsius. Minus 290 degrees Fahrenheit. So cold that methane exists as liquid, forming lakes, rivers, rain. Titan has a methane cycle like Earth's water cycle. Evaporation, clouds, precipitation, erosion. An alien version of Earth's hydrological cycle, but powered by methane, not water. 2011. Scientists analyzing Cassini data discovered something strange. Titan's atmosphere doesn't rotate with its surface. Titan is tidally locked to Saturn. One face always points towards Saturn. Its rotation period, 15.95 days. But its atmosphere? The upper atmosphere rotates in just 9 days. That's 1.8 times faster than the surface. Superrotation, like Venus. But Titan's atmosphere doesn't just spin faster. It wobbles. May 2024. Research published in the Planetary Science Journal analyzed 13 years of Cassini observations. Discovery: Titan's atmospheric circulation doesn't stay aligned with Saturn. It wobbles like a gyroscope, precessing around Saturn's equatorial plane with a period of about 1 year. 1 Titan year equals 29.5 Earth years. The atmosphere acts like a spinning top. It has angular momentum independent of the surface. As Titan orbits Saturn, tidal forces from Saturn try to pull the atmospheric circulation into alignment. But the atmosphere resists. It wobbles. This is the first time we've observed atmospheric precession on any world. Titan's atmosphere is driven by seasonal heating, like Earth. But Titan's seasons last 7.5 Earth years each. During Titan's northern summer, the North Pole receives continuous sunlight for years. The South Pole sits in darkness. Temperature difference drives winds. When the Huygens probe descended through Titan's atmosphere in 2005, it measured wind speeds. High altitude, 120 kilometers, 100 meters per second, 360 kilometers per hour. Near surface, 0.3 meters per second, almost calm. Extreme wind shear. The atmosphere moves fast at altitude, slow near the ground. And just like Earth, Titan has weather. Methane clouds form at high altitudes. Methane rain falls. Rivers carve channels. But unlike Earth, where weather happens quickly, Titan's thick atmosphere and low energy input make everything slow. Storms can last months. Seasonal transitions take years. 2024 analysis of Cassini data revealed atmospheric waves, large-scale oscillations in Titan's atmosphere similar to Kelvin waves and Rossby waves on Earth. These waves transport energy and momentum, shaping Titan's circulation. Titan is Earth's atmospheric twin, but running in slow motion, on methane instead of water, with an atmosphere that wobbles like a gyroscope. Alien, but somehow familiar. Saturn's North Pole has a hexagon. Not approximately hexagonal, not kind of looks like 6 sides if you squint. A perfect hexagon. Each side, about 13,800 kilometers long, wider than Earth's diameter, 12,742 kilometers. Wind speeds along the hexagon's edges, 320 kilometers per hour. First observed by Voyager 1 in 1981. Still there when Cassini arrived in 2004. Still there when Cassini's mission ended in 2017. Over 40 years, same hexagon, same shape, same location. Atmospheric phenomena aren't supposed to form geometric shapes. Circles, yes. Ovals, sure. Spirals, common. But hexagons? 2010. Researchers at Oxford University recreated the hexagon in the lab. They placed a cylindrical tank of water on a rotating platform. In the center, they created a fast-spinning jet, mimicking Saturn's polar jet stream. As they increased the speed difference between the central jet and the surrounding fluid, the boundary became unstable. Waves formed. 6 waves, creating a hexagonal pattern. Why 6? It's a standing wave pattern, a Rossby wave. The number of wave peaks depends on the speed difference between the jet and surrounding atmosphere, the size of the jet, the planet's rotation rate. For Saturn's conditions, the math predicts 6 peaks, a hexagon. 2018, analysis of Cassini data revealed the hexagon extends at least 300 kilometers deep into Saturn's atmosphere. It's not a surface feature. It's a towering column of rotating atmosphere, shaped by wave dynamics, stable for decades. Between 2012 and 2016, the hexagon changed color, from blue to gold. Why? Seasonal change. As Saturn's North Pole transitioned from winter to summer, increased sunlight triggered photochemical reactions in the upper atmosphere, producing hazes that changed the color. The hexagon isn't unique to Saturn. Lab experiments show you can create hexagons, pentagons, or other polygons by adjusting the parameters. Saturn's atmosphere just happens to have the right conditions for 6 sides. Every planet with an atmosphere has polar vortices, regions where air circulates around the poles. Earth has them, wavy, irregular jet streams meandering around the Arctic and Antarctic. Jupiter has them. Cassini and Juno revealed multiple cyclones clustered at each pole. 8 around the North Pole, 5 around the South. Saturn has them. A hexagonal wave pattern at the North Pole, a hurricane-like vortex at the South Pole. Atmospheric dynamics follow universal laws, but the details, the shapes, the speeds, the patterns depend on each world's unique conditions. Rotation rate, internal heat, atmospheric composition, seasonal cycles. The result? Weather from hell. In infinite variety. We've seen 5 worlds, 5 types of extreme weather. Jupiter, a storm lasting 190 plus years, powered by internal heat and fed by smaller storms. Jiggling, shrinking, but persistent. Venus, an atmosphere moving 60 times faster than the surface, driven by thermal tides from day-night heating, accelerating mysteriously. Mars, dust storms engulfing an entire planet, powered by seasonal heating and a positive feedback loop. Thin atmosphere creating global chaos. Titan, a methane cycle mimicking Earth's water cycle, with an atmosphere that wobbles like a gyroscope. Slow-motion weather on an alien world. Saturn, a geometric storm shaped by wave dynamics, a hexagon that has lasted 40 plus years. What connects them? Three factors drive all planetary weather. 1. Energy input, solar heating, internal heat, tidal heating. Energy creates temperature differences, and temperature differences drive winds. 2. Rotation, Coriolis effect, deflects moving air, creating spin. The faster a planet rotates, the stronger the Coriolis force, the more organized the weather patterns. 3. Atmospheric properties, thickness, composition, whether there's a surface. These determine how energy moves through the atmosphere and how long storms can last. Earth, water cycle, moderate rotation, solid surface. Hurricanes lasting days. Jupiter, internal heat, fast rotation, no surface. Storms lasting centuries. Venus, slow rotation, thick atmosphere, thermal tides. Super rotation. Mars, thin atmosphere, seasonal extremes, dust feedback, global storms. Titan, thick atmosphere, methane cycle, slow rotation, gyroscopic wobble. Saturn, fast rotation, wave dynamics, internal heat, geometric hexagon. Same physics, different worlds. Infinite outcomes. Earth's hurricanes terrify us. They kill thousands, destroy cities. But they're fragile, temporary, localized. Elsewhere, weather doesn't end. Jupiter's storm has raged since before your great-great-grandparents were born. Venus's winds circle the planet every 4 days, forever. Mars's dust storms can engulf an entire world. Earth is gentle. Not because our atmosphere is weak, it's not. But because we have oceans, land, surfaces that break storms apart. We have moderate rotation, moderate energy input. We have liquid water, which stores and releases energy, but in a cycle that resets. Remove those constraints, and weather becomes eternal, geometric, planetary scale, catastrophic. And out there, on exoplanets orbiting other stars, weather gets even stranger. Tidally locked worlds with permanent day and night sides. Hot Jupiters with winds reaching 2,000 meters per second. Planets where it rains molten glass, sideways. But not all worlds have weather. Some have no atmosphere at all. Mercury, lunar, airless, silent, frozen in time. Their surfaces haven't changed in billions of years. Except when rocks fall from space, at 20 kilometers per second. Weather shapes atmospheres, but impacts shape everything else. This is Cosmic Canvas, where we reveal the forces that shape worlds. From Earth's fragile hurricanes to Jupiter's eternal fury. From Venus's super-rotating nightmare to Saturn's geometric perfection. Weather is chaos with rules, and every world writes those rules differently. Until next time, look up during the next storm, and remember, it could be so much worse.